password before. Okay, and then slides look as they should, right?
Yes.
Okay, then with that, yeah, pleasure to be here. Really happy that you guys invited me. And so I'll talk. Hey, first off, I want to say that this is not just talk about my research. It's going to be part tutorial, and then towards the end, more some overview of some of our recent research in HPE labs. And I also need to give slide credits to a couple of people. I listed them on the slide. Most of the slides have been made by Fabian Boehm, but there's also a couple of other slides by Xian Xiao, Vincent Toussaint, and Stan Shang. So yeah, I think I'll immediately dive into it. I do know that this crowd is pretty well versed in optical computing, but I think it's still useful because there's going to be a couple more junior people online as well, to talk longer about the motivations, and that's actually what this talk is about. Like the initial section, at least, we'll talk about why do we want to do optical computing and what are the challenges and so on. And so a big chunk of my talk will just be about that. So I hope, yeah, there's like a bar on my side that maybe I hope that I'm not sharing, but can you see the titles on the slides or no?
Oh, I can see the title.
Okay, then it's just on my end that things are looking a bit messed up. Um, so yeah, the idea is that obviously with digital computing, we've been having decades of progress at the usual pace, but lately that's not really that easy to do anymore, and and because of that, like you see a lot of companies looking into alternatives, both big companies as well as startups. Um, and we see quite some investment in alternative computing possibilities, such as like people looking into quantum computing, where there's like a lot of funding has gone through that topic for quite some years now. And so, yeah, first question that I want to answer is like, why are we even going to alternatives for digital computing? And then after we address that one, like, what is the role for optics to play in these alternative computing schemes? So if we first go to why do we need something else than digital, I guess there's really a lot of different ways to show this, but it always boils down to something similar, like the thing that you see in this slide. It's something that our marketing departments made a few years ago. So some of the data is, I would say, already outdated, but the concepts are the same. Basically, if you see the amount of data that is generated in the world and predicted to be generated, like you see that it's really exploding because like you have a lot of sensors that are generating data. There's the Internet of Things. So these trends are there. And like, yeah, we want to process that data and do something useful with it. In addition, we also see these emerging worlds of AI, generative AI, which is not yet listed on the slide, but like the model parameters in AI models is clearly also exploding. And yeah, there's a gap between what traditional digital compute can do because it's stagnating and what the needs of both the generated data as well as the compute models that we're working with in AI. And so for us as researchers, that's kind of the opportunity we want to work on because this gives us some incentive to find solutions to close that gap. Why is digital struggling a bit? Well, there are three different ways to think about it. One thing that obviously is very important is this scheme or the computer architecture concept of the von Neumann computing bottleneck, where nowadays in digital compute, you typically have often the processor is separated from the memory array, and then moving back and forth data between these two things is going to give you some latency and energy efficiency penalty. Moreover, to allow for scaling in the usual way of Moore's law, at some point, we really need to increase the density a lot, and you get like at some limits of physics, causing engineering problems, causing commercial problems. It gets really not cost efficient anymore to scale down more and more and more because yeah, it's just impossible to do these things in the way that we've been doing things over the last decades. And so linked to that with these physics problems, there is also the thing about small device leakage, which actually prevents us from keeping on increasing the clock frequency. That actually is already something that has stagnated for quite some time now. And so all these things have an impact on what you can do in a single CPU. Realistically, in the next couple of years, we see that we need to think multi-core instead of single core. There are some other things that we need to do, and then it's not just about like trying to do the same thing as what we can do with CPUs on novel types of hardware, but maybe also we need to rethink the way that we compute. And basically, the idea there is that like there is really some incentive to look more and more into accelerators. Accelerators being types of hardware that can solve very specific types of problems very efficiently. And so there's this trend of like shifting workloads from CPUs to GPUs, where you can do parallelization. For instance, for AI workloads, we have a lot of matrix vector products that you need to execute in parallel. GPUs are obviously a great fit, as people have recently realized. Now, for some workloads, maybe you want to squeeze out even more juice and be even more energy efficient, and maybe you want to look at FPGAs in these cases, because you can then program your logic units in a desired way. And if that works well, and if you have a commercially interesting use case and the budget and the time, maybe you want to develop like an application-specific integrated circuit. So that's like the most efficient and you can go with digital. But in general, this is a trend that is already ongoing. Like we have tensor product units and things like that for AI workloads. But we see a shift from general purpose to specialized tools because that really can give us quite some efficiency benefits in speed or energy. And so what is this presentation then about? It's like, okay, say that we are moving to accelerators. We obviously also want to think about like which accelerator types are tasks are out there for us to investigate. Apparently, IEEE came recently with like a couple of grand challenges, so 8 topics where apparently developing accelerators would make sense. So for all the people working in optical computing, we might benefit from looking into all of these and seeing whether we can be creative and leverage and provide some of these devices. I think in today's presentation, I'm probably similar to some of the previous speakers. Mainly, I'm going to focus on machine learning, optimization as the main topics. But to make a case that looking into these accelerators can be useful, obviously for the AI accelerators, if you just think about NVIDIA, like because the stock market has realized that AI has a really good fit with GPUs, their value has exploded with a 20x since 2019. So there's quite also some commercial interest there and not just an academic interest in developing various accelerators for different types of problem classes. So, okay, these are the goals. And then how could you do it? There's also like quite some choices. I'm not listing all of these. But some I've already name dropped quantum computing. Obviously, we're going to talk about the optical computing, but there might be some exotic things like DNA computing. In-memory computing is also a work that is pretty important, like this thing to break the von Neumann bottleneck by bringing the processing close to where the memory is, like really where the memory is. And then there's also this concept of Ising machines that has been explored in photonics for optimization problems. Um, so Ising machines and optical computing, that is what I will mainly be talking about. So that's the context of why we need accelerators, which accelerator types that we want to have, and then the question is like, why optics, right? Before I dive into that, there are like some choices that we need to make. The thing that I first always want to refresh is the fact that like there's different ways to encode information. The one that we all know is digital computing, where you represent information in bits. Then there's this fancy thing out there called quantum computing, where you have like qubits, where like the qubit can be simultaneously have a probability to be in a 0 or 1 state. But the moment you look at it, then it's going to collapse into one of these two states. Before it, it's like a probability that it's in either one of these states. And you can design clever algorithms that leverage this and then get some efficiencies, for instance, for integer factorization or things like that. Now, in this presentation, I'm mainly going to talk about analog computing because I think that's really where there are some benefits for optical computing potentially in the near term. And I'm not going to explain this in a very rigorous way, but like a naive way of looking at it is to think about like, okay, with bits, you need a device to digital computing, you need a device to represent a bit. With analog computing, you would take the same device and try to represent more states, and then design algorithms that leverage that capability in a clever way. Also in ways that you don't really suffer too much from the fact that if you work in analog computing, you might have noise and there might be downsides there, but maybe there are ways to deal with it. So it's not just having the black and white state of a bit, but it's also having the whole grayscale in between the 0 and the 1 and do something clever with that, hoping that gives you speed and also energy efficiency benefits. That is not to say that people have only restricted themselves to analog computing. There is quite some work on quantum computing out there. This is like on the right, I show a picture from an experiment that has been done like 4 years ago. free space setup in this case, which was pretty awesome. On the left, I'm showing a print screen from a very recent paper by a collaborator of ours in the European project, Archetonics, a startup that is going after the goal of making an all-optical CPU. So great challenge. I'm not jealous that I'm not jealous of them that they are solving this challenge because it seems to be very, very difficult. But at least it's like some outline of why they're that what might be in their opinion an interesting idea to look at. So if you want to know more, then check the paper at the bottom left of the slide. It's on archive. Um, but okay, so for here, this presentation will stick for now into this world of analog computing, and then still you need to make another choice. You have a choice to make between like, do I stick with a fiber-based setup? Do I stick with a free space setup, or do I work with integrated chips? These are like the three traditional schemes of experimentally handling optical computing. Now, we in HPE Labs, we typically work with integrated chips. That's probably a lot of what I'm going to talk about will be from that perspective. But that's not to say that these other schemes are not interesting. I would actually say that all have their benefits and they've all been investigated over the last 60 years of optical computing. For free space optics, you again see that experiment from the quantum computing world at the bottom of the slide, like another one as well. I would say there's quite some advantages that like you can work with the third dimensional flight, and we'll get back to that later on, and that might give you some benefits to do certain things that are harder to achieve in native 2D systems like integrated chips. So that's like an interesting way where these approaches are complementary. And then the fiber-based setup with time division multiplexing, you can also do interesting things. And I would say that it's like the easiest thing to get experimentally something off the ground and running, but off the shelf components. So if you want to do an experimental demo, it's typically a good idea to look into fiber-based setups if you want to be fast, because if you want to work with chips, maybe you need to wait long time for tape outs, do the fabrication. It might, uh, be a bit slower than ordering devices that actually already are there, connecting them with fibers and demonstrate something there. Simultaneously, also with free space setups, there's like this issue that aligning a lot of lenses and whatever can also be very time consuming and finicky. So that's the drawback of these approaches. Um, Okay, so this is about the choices, so encoding scheme, type of setup. I still didn't really talk about why it might be a good idea to do this at all. So we listed to four prominent reasons that we had in mind when we are looking into optical computing ourselves. One is wavelength division multiplexing, or just the ability of a light to do multiplexing, because that might allow you to run parallel compute tasks in parallel. Obviously, this is something that we stole from the communication world, right? Like, why is optics so good in communication? Also because we can do multiplexing. Like, if you just compare the cross-section of a fiber where you can get a lot of wavelengths simultaneously through, and compare it with the same volume that you would need of coax cables to represent the same information, it's like a big difference. And that's something that Light is really good at, this multiplexing capability. And so we hope to leverage that as well in the computing instantiations. Then the other thing that is similar to communication is like light, when it goes through material, typically it can be low loss, so that might give you some energy advantages as well. There is some outlook for fast switching capabilities, but we need to be a bit careful there because, in a sense, when we think about optical computing, then we might work with more exploratory technologies. And also, if you then say, oh, this can be better in photonics compared to electronics, that's something that we could say. But also in electronics, there are ways to go beyond switching in silicon. And if you go to other materials, maybe the benefit that we have in optics compared to these other materials might be less. So we need to be careful in that claim there. Then finally, I also already mentioned multiplexing in general as a benefit. There's a spatial multiplexing, and this is like something where indeed we can represent larger amounts of data in a small footprint. Definitely if we think about free space setup. So that's like another ingredient that we might want to leverage when we are looking into optical computing. Now, there are more reasons. I forgot the exact number, but there's the paper at the bottom of the slide written by Peter McMahon, Physics of Optical Computing, and it contains like a whole laundry list of possible reasons why it's a good idea to look into optical computing. So for everyone who hasn't read it, please do give it a read. I think it's a really nice background paper to get yourself motivated of why you want to look in this field and how you would want to approach this. That being said, like I talked about the benefits, but then you can also wonder why isn't this already deployed? Well, there are some reasons why it's challenging to do optical computing. Some of these reasons are listed on the slide. One is pretty fundamental. When you think about optics, we have like the wavelength of light. If you compare it with the Brugge wavelength of an electron, and you convert it in some kind of a density to just get a feeling of the difference, and you see that obviously in microelectronics, the density is going to be way better than for photonics, and we can consequently squeeze way more devices into a certain volume than for photonics would be the case. So that's like a drawback that we have that might be harder to get rid of than we want. Then another thing, and this is actually something that is general for analog computing. So here I'm already making a choice that I'm going to talk most of the time about analog computing. We have a bit resolution issue. Like if we don't work digital, at some point we need to see how our signal is compared to the noise. The signal to noise ratio is important. And also, like we might need to convert sometimes our signals to the digital domain again for intermediate steps. And these ADCs, their power is going to, and the optical power related to that is going to scale exponentially with the bit resolution whenever you convert to digital. So that is a pretty fundamental thing that we again can't get rid of. Now, apparently, in some use cases, we can get away with low bit resolution, but that's not always a given. So it's something that we should be very mindful about. Then optical memory, there are devices that have been investigated that can give you memory capabilities, but they're not as scalable typically or that easy to interact with as people can do in electronics. So that's a bottleneck because that might like give you either you need to go to the electronic domain again to access memory, or you need to rethink your architecture and look for use cases that don't suffer from not having too much access to memory. And again, like whenever you go to the electronic domain, then you have an analog to digital conversion that you need to be mindful of. Finally, there are again a lot of nonlinear effects in the photonics, so that's great, but they can be pretty expensive because like why do we have low loss in photonics in the first place? Is because we don't have too much interaction with the material, and then when you have nonlinearities, you actually want to have a lot of interactions with the material, and so that's like the other extreme, and combining the two at the same platform, the same chip, might not always be easy, and so there's often trade-offs that we need to make, and so that makes it harder for us to get logic operations compared to the ones that you can get in electronics. I've mentioned about pros and cons. One thing that I now want to point out and is that like there's maybe lessons we can learn from looking into quantum computing. There as well, people have been making claims about, oh, if you build a quantum computer and you solve this problem with this algorithm, then you will have like orders of magnitude benefit compared to digital computers. And there's, a few years ago, we had this whole debate about quantum advantage that was out there. There were a couple of nice experiments, and then people were trying to catch up from the more digital hardware community, and they looked really into these physical instantiations, and they checked whether there were like corners that they could cut based on the specific implementation that was chosen, and typically that was indeed possible, and then they were able to enhance the algorithms and reduce actually the benefit of quantum computing hardware versus, for instance, classical supercomputers. And so that fight is actually, it's like actually pretty motivating. Like whenever you do something in a novel exotic hardware platform, you have the digital community that is trying to catch up. And that actually gives you also more motivation in the original platform than to do, again, even better. But so why am I mentioning this example? Not to trash quantum computing, but mainly to actually say that this is the same thing we probably should also do for optical computing. We don't need to say that we are better than digital. We really need to be careful and also make sure that like we give the digital community also the best, let them do the best job to on a certain algorithm or a certain use case that we're trying to investigate. And we might have some surprises there when we do this. And I think we actually are starting to get better in doing this. So I'm going to give an example of like one thing that recently has been mentioned by a person called Chris Cole, who has gone to a couple of conferences lately and also wrote a paper that is cited at the bottom of the slides, and where he makes the case that we really need to be mindful when we say that optical computing is better than alternatives. And his take is that, okay, and there's more examples in the paper. I'm really summarizing it on one slide. But his take is that if you compare electronic computing with optical computing, and you really want to be sure that there is an advantage of optical computing, you first off, maybe you want to also allow electronic computing to use optical interconnects if you assume that optical interconnects are better than electronic interconnects. So that's the first assumption he makes. And that's then already behind what the figures that you see on the slide. And then he takes here this example of like, okay, you can do electronic addition. So you come in with optical data, you convert it to the electronic digital domain with ADCs, TIAs, and then you do the electronic addition. Great, you've done your electronic addition, and then how would you do this in optics? One way of doing things is that you come in with a couple of different wavelengths, they hit the same photodiode, and then automatically, because of the physics, you do your addition. And then only then you do your conversion to the electronic domain and you convert it to the digital domain. So one catch could be that you say the analog to digital conversion is the power hungry thing. So if I count the number of ADCs that I have on the left, then I see that I have N for N input sales. And then I have like one ADC on the right. So optics is better because you have less ADCs. That could be something that you want to say. However, he says that's not true, because if you really do an apples to apples comparison, then you check what the bit resolution is on the left and on the right, then it turns out that you need an ADC that is actually better, that needs higher bit resolution for the system on the right. And so if you take that into account, then apparently this single ADC here is also going to become more power hungry. That's because of the exponential scaling also that I was talking about before. And that actually causes you that causes this thing that apparently having the ADC here, this one is going to consume as much power as the N different ADCs on the left because they have different bit resolutions. So we should be very mindful there, because then actually the benefit of doing the addition in the electronic versus the optical domain, it's pretty negligible. It's actually all the ADC that is like the bottleneck, and there might not be an actual benefit in moving to optics in the way that this is described in this paper. So that's something that we should take into account when we think about optical computing for sure. Then another thing to be mindful of, and that's actually also work that the organizers of the seminar are very much thinking about as well, not this specific paper that I'm listing here at the bottom of the slide, but basically in the field lately, there has been quite some progress in making photonic integrated chips, photonic chips that can do, for instance, matrix vector products. But like if you then really think about the energy efficiency, it's not good enough to just stick to the energy consumption of the photonic core. You also really want to think about what is around there, like the electro-optic conversion, the other way around. There's maybe access to memory. There's like co-processors you need to deal with. And if you really take the full system and you include all the different boxes that are out there, you might get these type of power breakdowns that I'm starting to see now more in the field. And what is, for instance, in this one interesting is that indeed you can see that the optics is only consuming a pretty small part of the overall power consumption. And that is important to know, because if then you as a researcher would say, the optics is still consuming X amount of watts or whatever of power, and I want to reduce it, you maybe want to first check whether there are other bottlenecks that you want to solve first. Like in this case, maybe the DEX and the ADC is what you really require your attention, and so on. And so I would advise people looking into optical computing to start doing more of these graphs. It's starting to happen, but I think there's still room for us to do a better job, and use that as guidelines for where you really spend your research time or for what you want to improve. And then this is also like one of the take-home messages of these graphs is that you need to think about data transfer, which can become pretty power hungry, and also like the electro-optical conversions whenever you need to talk to memory are also some things that often are not reported in older papers in our fields. So we should do a better job there, and then in that case, it might get become a harder comparison. Other things to keep in mind: general traps that people have fell into when you were looking into optical computing. And actually, I would say also even in our own research in HPE labs, we might have stepped into some of these traps ourselves. The first thing is like when we compare with digital, what we could do is like we run an application on a CPU or a GPU, and then we take the maximum load power of the CPU and we just compare what we do in optics with like this type of calculation, and we take the maximum load power. But often the jobs that we can run on our current hardware are so small that they don't consume the full CPU. So it's kind of unfair to really work with the maximum load power. And so there's like an app that you can use to remove the overhead, and like you run your application with that app, and apparently then you can actually remove the overhead and you really get like an apples to apples comparison. So that's like low effort on us, but it actually gives a better fair comparison. Then another thing is that like often people might forget that there's like an entire pipeline you need to think about. There's not only the thing that you can speed up with your photonic core, there's pre-processing, post-processing, don't forget to include that as well, because otherwise you might again be surprised that the thing that you actually try to improve might not really be the bottleneck anymore. Bit resolution, I already talked about it, that it's a tricky thing. The thing is also like if you compare, like often it's hard for us to work with higher bit resolution, so you want to go to lower bit resolution. So great, but then you can also do this in digital compute. And so if you can do it there might also be some energy efficiency benefits for them. And that also might reduce the gap between traditional digital and what we can do. And then another trap or thing that is maybe not always that straightforward to do is, or something that people forget is that like when you look at a piece of hardware, it's typically not just one number that you can squeeze out that characterizes the performance, like energy per operation, but also there might be latency or reprogrammability. There's like a whole zoo of perspectives that you can get on a certain piece of hardware. And typically it's actually good to talk about all of these different things because that really gives end users more feedback on why it would be a good idea or not a good idea to use your hardware. And so we should do a better job in reporting as many of these relevant metrics as possible. Okay, so I made my case there. Then obviously we can wonder like where should we use optics? The things that I'm going to talk about mainly in the following part of the presentation are optical interconnects, AI inference. I already talked a little bit about it, and also optimization, quantum computing. I will not talk about. But first, these interconnects. This is a little bit the bread and butter also of HPE labs over the last decade, I would say. We've seen this trend where like instead of just having systems that only had CPUs that were very homogeneous, we are moving towards heterogeneous computing systems or architectures where you have FPGAs, GPUs, these novel accelerators at some point. And we think an impact of photonics on compute is for sure also having an optical interconnect. And that's quite some of our research is actually going into that. And also Google TPUs, there was this paper in 2023 that already for TPU version 4, optical circuit switches were deployed. So you can see indeed optics as a communication tool has really an impact on compute, and that's something we should keep on pursuing in our field. But that's probably not really what most of the people on this call are going to think about. But yeah, just recap to remind you what HPE is doing. We typically work with silicon photonic chips where we come in with a comb source with a couple of wavelengths. We have a couple of microring modulators that are aligned to all the colors in the comb source, and then we modulate them one by one with using dense wavelength division multiplexing. We send all the information to a fiber, and then we do demultiplexing, send it to photodiodes, and that's like a typical transceiver module. And like we're doing this in silicon photonics because we think that it would be like cost efficient, and that's something necessary if you really want to deploy, for instance, an optical silicon photonic. Yeah, if you want to have an optical network in a high performance computing system, you want to be dirt cheap, and that's why scalable CMOS fabrication is crucial. So we've been doing quite some research on all these components you need for that, like lasers, modulators, grating couplers, amplifiers, and so on. There's like an overview paper at the bottom of the slide. And then there's also like some work by other people. This paper is a relevant one, where people see that indeed if you have optics in your network, silicon photonics specifically, then indeed you can get like network performance characteristics that allow you to, if you have very high bandwidth GPUs, there will really be a reduced time to accuracy. If you train a certain task on GPUs, the time to accuracy is really going to degrade a lot, decrease a lot if you have access to these silicon photonics components in your network. So that's already an impact that is there too. But okay, what we really want to talk about is obviously like actually computing a bit light. So for that, we want to do matrix vector multiplication. So we do multiply accumulates, like we have an input element that we multiply with a weight, and then we sum it with another element, and we keep on doing that. That's the basic ingredient for a matrix vector product. There's a couple of different schemes of doing it. Like in this, just to list one of them, you have like a couple of rings, a crossbar of rings. You align these rings in certain ways to these input wavelengths that you see here. And then the amplitude of the wavelengths is actually like how you encode the information. And if you just do check how these resonance wavelengths are aligned and they're either detuned or aligned with the input wavelength, and that's how you control the specific weight, then you can indeed see that the light that will hit the PD will express a matrix vector product. And this is just one way of doing it. There's like plenty of ways of doing it. Typically, we want to use multiplexing capabilities of light, high switching frequencies. We want to benefit from that, and so on and so on. And these ideas have been out there for quite some time. The hope was that we actually could increase energy efficiency, compute density with these schemes over digital. But like even already like 5 years ago, people were already saying that you need to be careful a little bit with these forecasts, because if you compare photonic compute with analog electronic compute, there might still be like some region where photonic has a room to play, but another region where maybe analog electronics is a more natural fit. And here, the idea is that like if you look into the bit precision, then apparently if you go to too high bit precision, then yeah, because of some of the fundamental properties of noise in photonic systems, you're going to see that the energy consumption is going to explode for photonics, whereas it's only happening a bit later for electronics. So that's the thing. Like for photonics, typically you want to go to lower bit resolution. The other thing is that apparently there's a benefit if you go to larger beta extracted products. All of this is explained in this paper, and there's actually a more updated analysis, I would say, by Alex Tate that is in this paper, which contains a better overview of all the possible noise mechanisms that you can have in photonics and like ways to calculate which one is dominant and what the limits are going to be. So then state of the art, I think most of you guys probably already know the 64 by 64 matrix vector product by Light Matter. Then there's like more recent work by MIT. I also know that one of the speakers, the first speaker, I think, of the 10-year series, actually was one of the co-authors of this paper, where like you had a couple of matrix vector products, nonlinear neural arrays, all on the same chip, and then with some outlook of like, okay, with current technology and technology that is feasible in the next couple of years, what is the energy consumption per operation that scales with the multiply accumulates as well. And so we got some really interesting numbers. And then the question is, what can you do with that? Like for us in HPE, we think that it's not a good idea to aim for general purpose AI as a use case. We think it's typically a better idea to look for certain niche applications where we can benefit from photonics being low latency, being able to work with high bandwidth, and so on. And some recent publications we really like are these two here. Like one is for RF blind source separation. So disentangling this, apparently you need quite some high bandwidth. And the idea here is also that it's not a pure photonic processing unit. It's more like something coming up with schemes where you have a photonic processor that is offloading some of the calculations that otherwise would happen in a digital signal processing unit. And by making this one smaller, the overall power consumption might actually have a benefit. So that is something that is discussed in this paper. And then similar things also have, or similar line of thinking is explained in this paper. And in this case, it's like this idea of, okay, optical data, you have optical long haul communication, to send as much information through your fiber as possible. At some point, you might have non-linearities. You want to compensate for that. Doing this with DFT is pretty power hungry. So can you do already some preliminary pre-processing that allows you to reduce the calculations that still need to happen on the DSP? So that is something that is explained nicely in this paper by the Princeton group. So these are promising things. And then another type of application that we also really like is this is not but it's a little bit linked in my mind to some of the efforts that we do with machine learning, but it's not exactly the same. It's looking into optimization problems. And so the line of thinking here is that like in physics, we know that like physics is pretty good in finding ground state. So we do this in a natural way. And we do this, for instance, in lasers. Like in lasers, you have some kind of a loss profile, and then you ramp up your gain. And the moment that your gain is touching, and I'm simplifying things here a little bit, like the minimal ground state of your loss profile, and the minimal point of your loss profile, then at that point, you're starting to oscillate in that state. So, and this is like a representation of all the laser cavity morphs. So that's like something that is naturally happening in lasers or similar optical systems. And so the idea would be like if you can program one of these energy landscapes yourself in such a way that it represents an energy landscape that corresponds with an optimization problem that you care about, then by identifying in which state your system starts to oscillate or resides, which ground state you take, you might have solved the optimization problem that you care about. So that's like the general link or analogy that we find between optimization problems and lasers. And so that's something that has been explored in a couple of different systems, and that's what that has been baptized in the field to be optical Ising machines, coherent Ising machines, or variations thereof. Like on the left, you see a general scheme where you have like time division multiplexing with optical nonlinearity. That is a degenerate optical parametric oscillator that has been used for that, that can solve these problems. There's like other schemes with injection of fiber lasers, going back closer to what I was listing on the previous slide. And apparently for certain problems with a certain number of variables in academic use cases, indeed, there was like a speed advantage that has been demonstrated. Also, worthwhile is the research that has been done where people compared for certain academic use cases. Like if you compare these classical optical systems that are finding ground states for certain optimization problems and you compare them with quantum annealers, then apparently that the success probability of solving problems is better than for quantum annealers like D-Wave. Reason being that quantum annealers, they work with qubits, and qubits, they need to be maintain their quantum states. For that, you want to isolate them from the environment, and for that, it's actually pretty hard for them to interact with a lot of other qubits. And that gives you actually some kind of limitation because you need to map problems to limited topologies like sparse topologies, and that gives you overhead and makes it not so scalable to map certain problems to this hardware. And that's something that we don't have in classical optics, apparently. So that's why these systems are pretty promising. And so I think in the interest of time, I might go skip the, or like, yeah, I can maybe just say there's like, yeah, there are various ways of doing things. And one easy way for me to understand what is going on here is that we see this as a Hopfield neural network. So that's indeed a neural network technique where you have an array of binary neurons. Then you have a matrix vector product, which we already know how to do this from the machine learning accelerators in photonics. And then you have feedback loops, which is also something pretty easy for us to do. And so, yeah, the crossbar array is like one way of doing it, but there's obviously many, many other ways of doing things. And with these two ingredients, you're able to make Ivan machines not only with oscillators, but also with bistable systems. And for the bistability, what you typically do is you have like some kind of a bifurcation parameter, a gain parameter, where you, if you have low gain, you don't have like an actual light output or something. But as soon as you cross a certain gain level, a threshold, then your state will either go to a state with a zero phase or a pi phase. And like if you don't see that, it will be randomly 50% in one state and 50% in the other state. So with this type of property, if you connect all these nonlinear neurons with the connection matrix, you can indeed, apparently, by controlling the weights here, you can control optimization problems. And the take-home message that I want to give for this community is that there's quite some work in machine learning accelerators on like these matrix vector units, that how to implement these efficiently. Lately, there's also some work on like making optical neurons, but apparently also for optimization problems, it's interesting to have some degree of programmability of your neurons, because if you wouldn't do it, you end up with a problem. That's actually explained in this slide. I know it's a bit of a busy slide, but the feeling is, the take-home message is that like the traditional way of having nonlinearities in these optical Ising machines is typically something that it can be approximated by a polynomial function. That is what is shown here. And if you ramp up your gain, then apparently in practice, you will see that there is some kind of a non-uniformity between the spin amplitudes and the other ones. Remember that we only care about the phase of the spin. It's a bistable system, and we only care whether it's zero phase or pi phase. The amplitude is in principle supposed to be the same, because if you don't do it, then apparently you're going to effectively program another problem. It's like going to be effectively a different connection matrix, because you multiply certain weights with an amplitude that is slightly different than somewhere else, and that leads to all types of problems. And so if you ramp up the gain here, which you need to do to go towards the ground state of the problem, then you see that your inhomogeneity is increasing, and it actually leads to very low success probability. Like you almost don't see the green signal here, and that's like green would mean that you have a non-zero success probability that you find the actual ground state for a certain gain level. For some other choices, which have saturation, like sigmoids, periodic nonlinearities, and clip nonlinearities, I'll explain in this paper here, you can see that indeed if the inhomogeneity is getting lower, then you get higher, there's a correlation with getting higher success probability. So this is some call to action that indeed we should look into nonlinearities that also have saturation, and having this type of programmable on-chip nonlinearities or optical systems, similar capabilities, would give you some benefit in success probabilities. Okay, then what are some trends? First off, we probably should learn from the analog electronics world. They are currently already having experimental demos where they have multi-core matrix vector product units of certain tens of TOPS per watt at certain bit level resolutions. There's two different demonstrations here from IBM and also I think one from Stanford. Typically in the photonics world, we have a range of TOPS per watt that is getting there, but like the experimental demonstrations are single, few core. We're definitely not yet at that scale. So we have quite some work to catch up with them. That's definitely ongoing research. I see already quite some simulations on how to get there, but I'm still waiting also for the experimental demos. Then other things, okay, if you go beyond what you can do in integrated chips, I already mentioned it a few times, but I don't mind repeating it. Sometimes you want to think about the third dimension, go to free space setups. There's quite some seminal work by Ryan Hemmerly a few years ago, where there was like some claim that if you combine time division multiplexing with free space setups and look for a certain noise regime that appears in photonics, then actually there might be some regime that you get energy efficiency that you wouldn't be able to get easily with analog electronics. So that's like interesting. There are some experimental demonstrations out there already, but it's still, I think, an ongoing challenge whether we can really keep on outperforming analog electronics. I'm not really sure yet whether I have already decided whether there really is a benefit or just a hope of a benefit. Then another approach is like, okay, instead of going to free space setups, try to be more three-dimensional in integrated systems by doing fabrication. There's quite some seminal work by Daniel Brunner on that, like very preliminary. I think there's quite some questions yet about like, okay, you can create these structures here for AI applications, but you still want to wonder how can you control and program them. So I expect in the next couple of years there will be some nice research that is tackling these issues. Then other choices you can make are if you have a matrix that you need to implement for an optimization problem or maybe for a machine learning problem, you might wonder whether you really want to implement all the elements in the matrix. Like say you have a neural network task, you trained your model, you have a matrix, you want to throw this to a chip. If you don't do anything special, then every element that you have in your matrix, you need some kind of a reconfigurable element on your chip as well to represent that information. If you just count the degrees of freedom, sometimes it's a bit more tricky than that, but overall the degrees of freedom, that's an argument you really need to respect. So another thing you could do is like you can take the matrix, you can do some kind of a decomposition method, you can approximate this matrix and reduce the elements that you need to approximately represent the information that you needed in the first place. And if you do that, you might reduce the number of elements that you still need in the end. Like you go from maybe from a million to a billion variables to 1,000 to 10,000 variables. And then effectively you reduce the elements that you need to control on a chip. And so that makes it again more feasible to represent bigger networks on the same chip surface. So that's a pretty promising approach. I actually will talk about it a bit later as well. We do it with tensor train decomposition methods and other ones, but there's also other approaches that are being investigated and that are worthwhile taking up. The whole idea is to sparsify your AI models to make them more scalable from a photonics perspective. And finally, another perspective that I also really like is that we believe in analog computing, that there are some benefits there. We think that optics has a role to play in compute, for sure, for the communication. We already talked a little bit about it. But maybe one thing that we should also be mindful about is like, why do we want to do everything in optics? Maybe that is not the goal that we should have. Maybe we can also have some part that is still analog electronics and do the things that are easier in analog electronics there, and then have some other things that are easier in photonics and work with such a hybrid approach as well. That is, I think, also a promising thing. There were some seminal papers on that as well. I'm still hoping that more people take up that idea and come with more experimental demos to prove certain things there. With that, I'll go to some of our own research. So I already touched upon it. Like we in labs, we have looked into optical interconnects. I talked about comb lasers that we developed them. We also have MOSCAP modulators. We have photodiodes, all these devices. For these modulators, I just want to mention that yeah, like typically what we noticed is when we make heterogeneous 3.5 on silicon laser devices, we paste gain material on top of silicon with an oxide layer. And apparently that oxide layer you can use as a capacitor. That controls the amount of charge that is there. You can sense that with a waveguide, and that actually gives you some modulating capabilities. Turns out you can also use a very similar fabrication flow in various ways to make memristors or trench trap flash memory. Memristors are tunable resistors. So what happens there is that like with these oxide layers, if you put large voltages over them, you can create ionic channels, and these ionic channels are going to control or change the conductance. Because of that, you will change the material properties. If you then send the voltage over it, you will control the charges that are there, and light will sense this, and it will also be able, you will be able to tune the phase or similar things in your photonic device. That's what is demonstrated here. Charge trap devices are like in some of our oxide stacks, we have a couple of different layers. If you check the Venn diagram of these things, you can see that you can indeed trap charges like similar to flash. Um, and then again, like light can sense it, that you change the material, and you can also, in a non-volatile way, in both cases actually, you can control the properties of light in the materials, and that gives you some capabilities that you can leverage when you are dealing with photonic devices in, for instance, a matrix vector units or product units or things like that. So this work has been published in a couple of papers lately by us and collaborators. Like some of the papers are at the bottom of the slide. But this is like a table that I took from the most recently published paper on the memristor technology. I should actually have put that in the title of the slide. But you can see that we can get pretty decent switching speed compared to alternatives that are out there. So that's good for when you want to do training on chip. Switching energy is also decent. Retention time is given competence, like not compared to charge trap, but compared to some of the other alternatives. The retention time is definitely also pretty decent, although yeah, there might be pros and cons for this device, dependent on whether you need a lot of retention. And this again is like an example of where actually you really want to list a lot of metrics, just because in certain applications you might care more about certain metrics than in certain other applications. Also, insertion loss is pretty low, which actually makes it a little bit of a scalable, and it will allow you to work with this in a scalable way. And similar table could also be found in latest, one of the latest papers by one of my other colleagues. This is work by HPE, where we compare to other charge trap or flash devices. One of the drawbacks of flash devices is that it's pretty low switching speed. So this is not something that you would use for training. You would have a trained neural network, then you deploy it and you want to use it for inference, but not the other way around. But on the upside, like actually the retention time is actually pretty good. So that's again like proving this point, like dependent on what your use case is, one choice might be better than the other one, and it's not really upfront clear which one would be best for all possible use cases. So that's for what we do for material research. There can be clearly a whole tutorial just on these topics as well. Then I promised you a little bit of more of a deep dive into these tensor train decomposition methods, and I'm also keeping track of time a little bit. But so the basic idea I already explained, like you take a matrix and you want to just reduce the number of elements that you need when you map this to a photonic device. So what is the whole flow that we do apparently for the tensor train decomposition method, which is the one that we first explored in collaboration also with UC Davis and later on also UCSB. You reshuffle the elements in your matrix by creating a tensor and just creating additional dimensions. So this is not adding more elements, it's just like putting them in a multi-dimensional tensor instead of a 2D matrix. And then once you have done that, you can apply existing tensor train decomposition methods, which apparently are going to represent this matrix with a product of a couple of different tensors that are, in this case, 4-dimensional by nature of the algorithm. And the idea is that like these tensors contain also a couple of elements, and if you would sum all the elements in all these tensors, then the total sum of the elements should be less than the total elements that you had in your original matrix. So that's the idea. And I know this is pretty abstract, so it's probably easier to explain this with an example. So we have like this matrix here, 4x4 matrix with a couple of elements. You can follow the colors. And here we first fold it. So we introduce additional dimensions. We make a 2x2x2 tensor out of it. We didn't change any information. But then what we do is we apply this decomposition method and we approximate this 2x2x2 tensor by tensor product by these two tensors that are like clearly contain less elements in total than what you have here. If you would multiply it out and you convert it back to a 4x4 matrix, then you can see that this thing is indeed approximating this 4x4 matrix, but it's an approximation. So you do make an error. And then the question is this approximation good enough? And so that is something I will address in the next slide. But so to remind yourself, usually with MZI meshes, you typically have like a couple of laser modulators, single wavelengths. Like you come in with laser, you modulate lights at a couple of inputs, you do spatial multiplexing, and then you have PDs that are measuring the outputs of the MZI mesh, make spectral product. What we do if we apply this approach, we get something way more complicated. All the details are in this paper here, but the overall number of elements that you need should be lower. And if you then check first, what is the impact on the accuracy of your neural network task? For this thing, we work with an MNIST handwritten digit classification thing, where we count the number of MZIs that you need, and you check how the accuracy is changing. So without our approach or a similar approach, that's the black line. If you have too low number of MZIs, the accuracy is really going to go down. Like if the number of intermediate neurons in your hidden layer is too low, you fail. With our approach, you can actually go to way less MZIs and still get decent accuracy. You have a penalty, but it might for certain applications be okay. And this is like another baseline that is explained in the paper as well, that it's doing a good job as well, but there's a bit of a penalty compared to our approach in the simulation that we were doing back then. So if you compare then our approach in photonics with analog electronics, then you see with our approach, because we have the footprint of light issue, we need to apply this approach. In analog electronics, you wouldn't need to do it, but with this approach, there is some hope that indeed we can catch up with analog electronics and get similar figure of merits like that are taking into account energy consumption as well as footprints. So yeah, that's like one take-home message from that part of research. And then the last part of research I want to talk about is this on-chip training by the same researcher, Chen Xiao, one of my colleagues. He is looking into, can you actually do on-chip training in photonics? There are some experimental demonstrations out there. That's what you see on the upper right of the slide. And there's some reason to do it because like on chip, there are some deviations between the hardware and your software model that leads to degradation. So you might want to do it on chip, but like doing it really on chip comes with a lot of penalties. Getting access to the grading system or some. You might need to do a lot of OEO conversions. You might need digital analog conversion as well. So latency, energy bottlenecks there. So because of that, people are looking into other techniques. One technique that has been proposed recently at UT Austin by some very familiar authors is looking into the zeroth order optimization technique, where you only do forward propagation inference on your neural network, but you use that to approximate your gradient, and you get some kind of you can do gradient descent, but with some convergence issues and maybe scalability issues. And so that is what we wanted to address in this recent work, where they were specifically looking into physics-informed neural networks for solving high dimensional PDEs. So in this application, there were some higher order gradients that needed to be calculated. So for that, by definition already, like backpropagation, the traditional way of doing things, isn't really a good match there. And so the idea was like, could the zeroth ordered methods be used there? And then also, when we would deploy this on an optical neural network, can we actually leverage the fact that we work with tensor decomposition to being even able to map our neural pin to our chip? And then does that have an impact on the conversion? And apparently, indeed, because we compress information, we apparently have better convergence, and that is actually explained in the next slide. So here you compare optical neural networks with this new approach. This is with hardware-aware training of chip, off-chip training, either with hardware-aware models or not. And then you can see that with on-chip training, by definition, hardware-aware training, you can actually see that you can get pretty good performance with this proposed approach, where you combine these on-chip training with optical neural networks and so on. And there's like two different flavors of doing that here. Like one is time multiplexing with a small chip, and then with some penalty in time, you can demonstrate this eventually experimentally. And for now, we only have simulation experiments results, and then we also have like the one where we use wavelength and space multiplexing. Okay, and then I think with that, it's time to wrap up, to leave a little bit of room for questions. So what did I talk about? I made a case for there's a reason to move from general purpose to specialized accelerators. There are some benefits to gain there, but while optics clearly has advantages for communication purposes, if we think about computation, we really need to do a good job and compare ourselves in a fair way to state of the art. And there are some dangers there, like we need to think about analog to digital conversion, optics to electronic conversions. If we do have these things a lot in our solution, probably we're not going to do a good job, because these are going to become some bottlenecks that are that will take away our advantage that we have by doing analog computing. Then integrated photonic AI cores have an issue with the footprint of light, so it will be very hard for them to scale to thousands of neurons unless we do something special. Data movements also will be something of a bottleneck. So there are solutions that we need to think about. Like as long as we need to move data to electronic memory, there will be issues. So we will need to do more research into that. And analog electronics is definitely always a thing that we need to keep track of whenever we propose something in photonics. And then I talked about 3 different research contributions of HPE, a bit, yeah, maybe randomly, because there is actually also more. But like we do a lot of work on non-volatile photonic memory, some recent papers on that. Then we have the standardized optical neural network approach, and then very lately there was this like fun paper about backpropagation-free training that also leveraging the fact that we use tensor decomposition. And I think with that I will leave the room for questions.
Okay. Thanks, Thomas, for the nice talk. It's very comprehensive on the state of the art of optical AI computing. And so I think now we are going to the QA session. And if anyone in the audience would like to raise a question, it's a good time to unmute yourself and ask the question to Thomas right now. I will pause for a few seconds to see if anyone wants to ask some question. Okay, so then I will go to the questions in the chat room. And so I think the first question is from Luca. So I think actually already this last page slide already covers this question, but anyway, I will repeat the question. Even if we say analog computing, we still need free-for-all digital circuits to make the system work. Say the memory block, and we also need digital analog converter, analog digital converter to convert between digital and analog domain. Would this cause a problem?
So yeah, I think I fully agree, and this is a thing that people typically in literature of like a few years ago were forgetting, quote unquote. But I think we're getting better as a field to address this, and I think it's something that we now start to keep in mind upfront whenever we propose a new computing solution. So yeah, fully agree that this is an issue, and I actually really think that if we want to do something useful and have an impact, not just do thin research, this is one of the main things we should think about. Next question.
Yeah. Okay, next question is from Yu Lin. For the less thermal management low losses, have a question that in some optical neural network implementations based on MZI, the heaters used for phase shifters are quite easy to be influenced by each other and by the environment temperature. Any idea or comment on this issue?
So I'm kind of curious from which slide or moment the question came from. So maybe first off, like I think the initial demonstrations of matrix vector products in integrated photonics was indeed typically done with heaters. Because that's the most mature technology, the most scalable technology, and that all made sense. And indeed, like if I understand the question correctly, there's like an issue with if you heat somewhere on your chip, you might have also heating in some of the waveguides that are nearby. That is very problematic. There are actually quite some papers already, like for instance, for microring systems, there are some papers in the Princeton group that are like giving ideas of how you can calibrate these things. It gets a bit tricky for sure, but there are ways to, from an engineering perspective, just deal with this. You know that this issue is there, you know how to model it, and then by doing appropriate calibration, you can circumvent it. That's on if you don't do anything specifically on the design of the heaters, then other things that you can do. There's also obviously quite some research into like, okay, maybe I can etch trenches around my heaters, and that might make it like reduce the amount of cross heating that you have between certain devices. But then I think actually in general, the field probably wants to move away from heaters in general. And so that's why we are doing all this research into non-volatile tuning, because a heater, and I didn't really explicitly say this, but under the hood, I hope that this is clear also to the people online that, okay, whenever you have a heater, you're having a resistor where you send a voltage, like you put a voltage over it, you send current through it. So you burn power, and that is something that is making these things very power inefficient, because then like your power is going to scale with all the elements that are in your matrices, so that's n squared for n neurons or something. So that is actually exactly the type of thing that we would like to program this. Then don't have any, would like not have to have any power consumption in our mesh when we're active, and that's for instance something that you could get with this charge type memory or the flash memory that I talked about. Like whenever you program these things, you're not really burning, you're not sending currents through these things, so you're not burning power. And there's like also comparable approaches with phase change memories and so on. And that's maybe the answer to the question, because if you use these approaches, also MEMS are, by the way, another alternative approach, then you wouldn't have that terminal crosstalk issue in the first place. The downside is that at this point, these technologies have been out there. There are some very impressive demonstrations there, but they're not yet that mature, and they're maybe not always accessible to every research lab. Like people have to do it in their own labs. Maybe not every pilot line foundry is already able to offer this to all the customers. So that's, I think, I hope in the next couple of years that people would start offering that more, because that's really where we need to be if we want to do something useful at all. Okay, so that's that question, maybe a bit long-winded answer.
Okay, the next question is from Samuel. Is area a problem? In digital electronics, people calculate area because usually power is closely related to. I think he means because usually area is closely related to power, but in integrated photonics, passive device don't consume power, only active device do. I mean, only a few portion of the area in integrated photonics will be active devices and consume power.
I like the comment a lot, actually. It's indeed something nice to think about, because when I started doing research with colleagues in HPE labs that are from the analog electronics community, they indeed also gave me the feedback that whenever I'm emphasizing figure of merits that are area based, then they were saying like, but we actually, why do you care about it? Actually, you already do this anyway, because we know we have a die, we know what within the die what you can get as a compute for memristive crossbar arrays or similar. And like just the surface is like also representative with the power consumption. So if we know the power consumption, we kind of also know something about the area. There's a lot of connections there that indeed are not happening in the same way for photonics if you work with non-volatile memory, as I was just explaining before for the previous question. But I wouldn't say that this is giving us an excuse to not care at all about footprint in integrated photonics, given that the fact like we still have like the finite size of the reticle. So what we can represent with a certain footprint will definitely be limited. So that's one thing we want to care about. And obviously, like it's not only about power consumption, but also about cost. Like if we're going to be building very large wafer scale systems that are in photonics that are maybe doing the same thing as what you could do with analog electronics in a single die, then probably our wafer is going to cost more than the die. And that is also going to take us out of the market. So there's also that type of argument that you might want to think about. In addition, at some point, if you go to very big systems, maybe there's actually going to be latency that you want to avoid. There might be also some things that, like, if you go off chip, you will have some power penalties because you need to have die-to-die communication, things like that. So it really brings a lot of additional, like, even though the initial idea might be that, okay, in the crossbar itself, you might be passive, you have low loss, so you might be safe. Well, as soon as you hit the boundary of what you can do in a chip and you need to talk to the outside world, you will hit penalties again. And so the overall picture might be more complicated than just ignoring it. So I would be very careful about it. And I think that's one of the reasons that we in photonics definitely should keep on caring about the area as a metric. Yeah, that's my take on that.
Yeah. Okay. And the next question is, can we integrate optical computing cores in HPC to work together with CPU, GPUs in the future?
So wait, I missed the first part of the question. The question was to have like a collaborative effort between optical computing efforts and then GPUs and TPUs or something.
Yeah, I think that's the question. So
Actually,
basically,
yeah, I for sure think this is kind of the way of thinking, and I hope that I shared it somewhere. This is the long-term vision that we have in labs indeed, that we know already that we need to think about heterogeneous computing. Sorry for too many slides. This is the system that the slide that I was looking for. This is a marketing picture, right? But it's still showing a little bit what we have in mind. Like, so we have the traditional CPUs, GPUs, and then we have research going into these alternative ways of computing, not only photonic, but also electronic, and also quantum computers at some point need to talk to classical computers to do their work, because like it's a combination of classical computes plus quantum computing plus qubits that is really doing the effort in quantum algorithms. So we do think that it is indeed beneficial to have systems that will have more variety in types of accelerators. And I think one of the ideas would be like if we think about a cloud access use case, like as a service model, then people who have a certain use case, they would maybe log into one of these hybrid systems, and then there would maybe be some kind of a software layer that is actually going to tell you, this is this type of problem. For this one, these accelerators are going to be useful, and maybe some of these are going to be in parallel. Like for some parts, maybe it's better to use my CPU for some parts of the algorithm, definitely for optimization problems that is typically appearing. And then for other parts, you want to have like something that is super fast but very dedicated, and then like you have some interaction between the two. And that's also why I think we need to keep on thinking about our interconnects, photonic interconnects, hopefully, but also actually about the pluggability of our accelerators. And I didn't really make that point. But if you're going to develop a new accelerator and you don't think about how that thing is going to fit into an ecosystem of other things like memory, I/O, or whatever, you're probably going to make something that could maybe give you orders of benefit on a certain niche type of an algorithm, but it wouldn't make an impact on the overall use case, because like in the end, you always will have to work in this type of ecosystem. So that's also something that I think we really have to think about from the hardware community, that we are mindful that we will need to talk to the outside world and potentially to CPUs, GPUs, or FPGAs. And it's also not only that, but it's also at some point we will need to talk more to people from the software community to make it like easier for them to understand what our hardware is and have some kind of a software stack that simplifies it for them to use what we have designed. Like every time we come up with a new type of hardware, like somebody who is developing a new AI algorithm needs to develop a new software stack to talk to your specific niche accelerator, then it's not going to work. Then it's way too much effort, and nobody, that's just not commercially interesting. And so that's why that's something we probably also should talk about certain standards of how these things should communicate to the outside world. Other questions?
Yep. The next question is the scalability of the ONN tensor cores limited by the size of the ONN hardware?
I actually think this is a really good question. And I think that I don't know the answer yet, and I would like to know the answer yet. So maybe, like, I'm pretty sure my colleague is looking into it, but if other people are interested to look into that question, then I would be very happy. Well, actually, I should probably not do it in this way. Let's just scroll to the right slide. So what are we talking about again? This is maybe a good one. Or yeah, the previous one. Like what is happening is, like, if you map this thing to hardware, then you get like a couple of crossbars, which are native crossbars that I've been talking about before, nothing special there. And so indeed there's a size limit there. So that is a constraint. But the thing is also, when we have our use case, we have a matrix that we want to deploy to our hardware, we need to follow an existing decomposition method that is transforming our desired matrix into something else. And it's like this type of test that is actually really going to tell us whether, with the constraints of the hardware, whether we will get a big penalty hit for the test accuracy or not. And that is a study that I don't think we've done. Like, so far we see that indeed, like for this example, for MNIST, like vanilla toy example that everybody starts with, it seems to work. But maybe for some other use cases, it's possible that your factorization algorithm is going to give you some other sizes that are very hard to achieve with photonics. And if that were to be the case, then maybe the solution wouldn't be very good. Or like, you might need to think about, like, okay, which dimensions am I going to shuffle into wavelength division multiplexing? Which dimensions am I going to shuffle into spatial multiplexing? So there's that type of trade-off. I think there's quite some more research to be done for this technique. But then again, I also am listing this as a thing that we are studying. I think the overall take-home message should be, think about decomposition methods. And there is a variety of decomposition that's out there. There might be other ones as well that are worth addressing, and maybe they can deal better with constraints that we have in hardware. Also, this problem is not too new in the sense like even in electronics at some point in analog electronics, you're going to get a finite size of your crossbar. So even then, they also need to think about like going beyond a certain crossbar size that is physically relevant because of noise constraints and whatever. And so there's quite some studies in that field as well. And I think some of these studies we can replicate and apply here as well. So maybe we would then do something like having tensor train decomposition on sub matrices that we implement, and then still have like some more traditional off-chip interconnects that are converting the information from one die to another one in the same way as it's typically done in analog electronic demonstrations nowadays. So I'm saying this as if it's easy, but it's actually really a lot of research that needs to be done, and I hope that some people are taking a look into it. Yeah, so that's my take on that question.
Okay, so I think that's the end of the question in the chat room. So is there any other question from the audience? Okay, then if no further question, yeah, that's the end of our seminar today. And once again, thanks Thomas for the great talk. It's very comprehensive, like including all the state-of-the-art works. It's really great talk.
Cool, thanks. My pleasure. And feel free to reach out if you have questions in the talk. I'm also happy to share more answers to questions, potential questions in an email conversation. Bye.
Okay, bye.